Welcome back. Now there is the hands-on session. So the speaker of this session is Paavo SEITSONEN, and he will introduce optimization, NAB, and automatic workflow. So these sessions, actually, there are also other tutors, Matic Bobernix, Unmesh Mondal, Felice Conte, and Tao Jiang, that will assist the participant for the exercise. There are some technical details that now I leave the word to Ivan. Ivan?
What?
Okay. Okay. Do you want to say something about Slacks and...
Yes, I wanted to say that since now we are going to use, for the people that are following on Zoom, since now we are going to use in this section, we start to use the cluster. So we start to use the HPC resources with these remote commands that you find in the script collection. If you have technical problem using this command, please write on the appropriate Slack channel. So if you look at the Slack channel we created, there is one channel called cluster ICTP Argo, which is the channel for the people that have problem running on the ICTP resources. There is a channel called cluster JSI Harness, which is the cluster for those that are using the resources at the in Ljubljana. And then there is the cluster SISA Ulisse channel, which is the one channel for the people that will use the resources HPC at SISA. Okay, so if we behave this way, we can keep the request appropriated to the correct channel, and we can keep the main channels clean for, let's say, scientific discussion.
Okay, thank you.
You're
welcome.
welcome.
For the explanation, and I think Harry, please, thank you.
So thanks to everyone. Thanks to the organizers for giving me the opportunity to guide this session. Special thanks to Tone, who has been helping a lot setting up this exercise, and I think it also originates quite a lot from the previous edition of the school. So I'm very thankful for also the tutors, and yeah, thanks Sandro for the introduction. So my name is indeed Paavo SEITSONEN. I'm working currently at the École Supérieure in Paris, and I think my first encounters with quantum espresso were maybe during my PhD time, which was last millennium. I mean, still when it was not pre-code, but so I've been working or using it quite a long time. But maybe a different aspect than what you see today. So please feel free to post the questions. So as you have learned, please use the Slack channel, preferably the day 3. And as Ivan mentioned, if you have any problems with the cluster, post on that channel of which you are assigned to the cluster. In principle, every one of you was already setting up access to cluster. We were testing that on Friday, day 0. If you have any problems, then please write that on that cluster section. So I guess that the tutors, they are following those questions also during my presentation. So the topic you have seen, it's about structural relaxation and the NAB, and then we will use more and more the PWTK also during this session. So the topics will be the structure optimization. We start with the relaxation of the atomic positions only. You will see the examples. Then we go also to the variable cell relaxation. So that will be the easy ones. And this is what, well, I would say most of the time people are doing. Then we go to the NAB method. And as Tone showed this morning, then this is, sorry, morning for us, maybe another time of day for you others around the globe. So what Tone was showing, how we can get saddle points, reaction paths, and so on. So we will have 2 very simple examples here in this part, and then all over the way, actually already before, we will have examples on using the PWTK, and we go more and more, well, let's say more and more also to the analysis toward the end. So this example 4 will be about some more specific features of these exercises. And then before we really start, I hope everyone remembers to do this git pull. So just to make sure that you have the latest version. For example, this document was still modified yesterday to this presentation PDF file. And if you had these modifications on some input files, if the git pull complains, you can try this these 3 commands. So if during day 1 or day 2 you had some changes, you might change or execute these commands instead of just git pull. So you should be then up to date. If you have performed, if you have any problems, then please report. So the next slides will actually be about something that we will use a little bit later. So I thought that we leave these, we don't go through them now, but in maybe half an hour or so. So first we go the simple exercises, and then we will use these remote HPC clusters. Like I said, I hope everyone was there on Friday. If not, then you managed to get in contact with someone, or you managed by yourself to set up the access to these 3 clusters. So you are assigned to one of the 3 clusters. So we hope that this works for you from the beginning. If not, then we will see with the tutors how to fix your problems. So we will come to these slides a bit later. The first exercises we will still run on the virtual machines, or if you have set up everything on your personal machine. And these are very simple exercises. These should be very fast to execute. So the first one is a derivation of something which looks like the graphene, but we modify it a little bit. So if you have well, sorry, I show you again. If you don't remember, you can go directly to the link on day 3. You click, and well, the hands-on, it's there, so you can open the file if you want. You can always, like Tony and others have explained, in every directory there's this README file, and then there are some other instructions here for the remote execution. So I have this PDF file which I was showing open already. So now we go to the first exercise. So if you click, you go into this directory on the file browser. You click on the right, you can open in terminal. So you directly come to this directory. You see it's the example 1. So we start here, and as usual, you can start by looking at the structure of the input files. Now there are 4 input files, but we start with the graphene one. So actually, there's the graphene 1 by 1, kind of just for reference, but you can have it look later if you want. So we now launch, or I will launch the code. I mean, I could reduce the dimensionality. Now you see what is the difference. If I don't reduce the dimensionality, then you see some atoms are above, some below, but maybe it is easier if in this case, sorry, I go back and we reduce the dimensionality, then it's clearer for you. So I reduced the dimension to 2D because this is a 2D system, and in the third direction, there's supposed to be enough vacuum so that these layers are isolated from each other chemically. So this is the structure. I will make some multiple copies of it just for the visualization. So the computational cluster will be just 4 atoms, but I show how it looks like. So this is the graphene plane. And as you probably all know, in graphene, you have this sp2 bonding. Now, if you put hydrogens, you kind of put the hydrogen where there's this lone pair pz orbital, so out of the plane orbital. And it is actually quite easy to understand that it's easier or better, it's preferable energetically, put the 2 atoms alternatively. So you put every second atom above, every second below this plane of the atoms. So we start from the flat plane of graphene, and then we will see what happens. So this will be the target to optimize the structure in this exercise. So that was the structure. Now let's have a quick look in the input. I mean, by now you are almost experts in the looking at the input. So now we have the calculation mode is relax. So this one, actually, I should mention that in this one, we are still keeping the lattice constants, lattice vectors fixed. This should be optimized. I see there's someone who is writing on the screen. So we should relax also the lattice constant, but this, to be things simple, we don't do it yet. Normally, in almost all kind of systems, you want to optimize the lattice constants or the lattice vectors, let's say. So then in the system section, we have a hexagonal system. So Graphene, you have seen it already. It's a hexagonal one. So we have here we use the convention of using the CellDM variables. So the first one gives the lattice constants. This is in hexagonal case now the lateral lattice constant, and this is in Bohr atomic units. So this is actually something like 2.5 Ångström, I believe, if I remember correctly. And then in the other direction, perpendicular, we have well, hopefully enough vacuum. So this is actually COA. So the length is 3 in the direction perpendicular to this plane is 3 times the value of this one. It is probably not enough, but this is to keep the calculations fast enough. So we have 4 atoms, 2 types of atoms. You see carbon and hydrogen. And then today we are not going to spend any time on optimizing the parameters. So we have chosen some predefined values for the cutoff energy K points and so on. You are now experts in choosing them. I must say that this might be a bit too low for some of the exercises, or certainly too low for some exercises, again, to keep the calculations fast enough. So if you would repeat this for a real scientific project, you would probably test all these and, like I said, converge lattice constant and so on. Then yeah, we have 2 kinds of atoms. We are using the ultra-short pseudopotentials, and we have the 4 atomic atoms in the unit cell. And we specify them not in the crystal coordinates, but in the allied coordinates. So all the coordinates are now in units of this value, the CellDM1. So you would see that in this case, well, this is how you represent the honeycomb lattice of graphene. So this is the value. This comes from, is it 1 over square root of 3 is the value, and then you would multiply it with the allied. And you saw it already in the input when we visualized it, so that gives the honeycomb lattice. And the positions are so that one of the hydrogens is just above the first carbon, and the second hydrogen is just beneath the second carbon in the unit cell. So this gives this alternating pattern, and this actually keeps also the very high symmetry of the lattice. So then we use K points, like I said, we keep them fixed today. If I may mention some historical remarks, I mentioned my PhD. So actually I was studying the translations of the K points. And now in this case, in the hexagonal cell, it's well, it's not obligatory, but it's much better to use the no shift, so-called no shift. So that's a historical. There was a discussion in the literature why there should be no shift, and that's actually to have a more symmetric set of K points. So this means that there's one K point which is at gamma, and then with this no shift, you will have a symmetric set of the K points. If you would use 1, 1, well, now there's a vacuum in the third direction, so in principle it doesn't matter if you have anything between 0, 1. But if you would put here 1, 1, 0, then you would see that the K points, they look a bit funny, so they will be symmetrized, but the original or the idea is to have the equidistant grid, and that's achieved without the translation. So that's why we have 0, 0, 0, basically always when you have a hexagonal cell. If you want to, you can check my PhD thesis in the appendices. I show how funny those look if you do the translation actually. And then we use 991 K points. It's again maybe not enough for graphene itself, for this so-called graphene, where you have this hydrogen. It's probably enough because you will see how the electron structure is different. So this is the input file very quickly. So then you can follow the instructions either in PDF file, or if you want more detailed ones, so you can have a look in this file. So this is the README file for this exercise, and the first exercise, here's the command to execute. And now, sorry, I forgot to mention, so the idea is now in the first exercises we will synchronize. So we try to keep sure that most of you, or every one of you, can follow the exercises. Then in the second half, after we have done this remote cluster thing, so then we leave you more freedom. You can take your time, and you can discuss with the tutors. I will of course be available, but at the beginning we try to keep you synchronized. So if you have any problems, please write immediately, and we and the tutors, well, me and the tutors, we can check if you have any problems. But this should be very simple at the beginning. So I hope we can keep everything synchronized. So here we did the execution of the command. Sorry, I made it a bit bigger. So this is just now we still run only with one core on the virtual machine, so a host machine. You could, if you have enabled multiple cores, you could run even parallel. I did initially. I ran some of the examples. I think parallel on the virtual machine. It depends on which kind of computer you have. So I launched the calculation. It's probably very, very fast. So it's very similar to what you have done before. So here it says running on one processor, which means on one core. So there was no MPI. And it was not compiled with OpenMP, no threading, and so on. So again, there's the standard output, or the normal output. You see the repetition of the most important variables here. And then the lattice vectors and so on, the pseudopotentials, k-points, so something that you have seen before. So now doing the relaxation, the output looks very, very similar as before. You see the system, the electron structure converges in quite few iterations. So it goes basically exponentially. So we need only 8 iterations to reach the convergence. And then the eigenvalues, you see, and then after the first step, or the first self-consistency, you see these forces. So this in principle something new. You might have seen the forces before if they were enabled in the output, but now of course the code has to calculate the forces, and Pietro explained this morning how they are calculated using these derivatives of the total energy with respect to the atomic positions. And the good thing, or one of the great things with plane-wave basis, is that the forces, they come almost for free. So byproduct, once you have the self-consistency, then it's very fast to calculate the forces on all the atoms. So those are, if you do relaxation, those come pretty quick, all the forces on all the atoms. And here you see already that the forces laterally are 0. So in the hexagonal cell, the xy, and this lateral plane, and these are 0. Well, you could ask, well, how come they're 0? Exactly 0 to so many digits? Well, of course, the answer is maybe obvious to you. The symmetry is so high that there are no forces lateral. So the atoms in the graphene, they feel no forces because they are symmetric in this honeycomb structure, and there's no lateral force. But we have forces vertical, and then on this, in the quantum espresso world, you know, these are the forces. It's also written here. They are in the Rydberg atomic units. So this would mean roughly that this would mean that if you displace one or this atom vertically by one Bohr, or one atomic unit, the AU, then you would gain or you would lose 1 Rydberg, and that's quite a huge force. But of course, the forces, these initial forces, they depend on the initial geometry. If you start from something which is very close to the final geometry, the forces will be small. Fine. So here, now it's written, so we didn't specify anything in the inputs. As Pietro explained this morning, this means that we will be using the BFGS optimization algorithm for the geometry. And it says, okay, now we have done one self-consistent cycle, and this is the 0th algorithm or displacement of the atoms using the algorithm. So after that, the atoms are displaced according to the forces, according to the BFGS algorithm, and we go to the next self-consistent loop. And now it converges, well, in 7 steps. Again, the eigenvalues, the forces, you might notice, okay, the forces were 0.2 something, first iteration, and now they're 0.1 something. And this was the second self-consistent cycle, and we have accomplished the first BFGS cycle. And we have the new atomic positions. Okay, and we would see that, okay, these forces are still too large. We cannot consider the structure converged. So that's the third iteration. Forces, again, smaller, 0.0 something, and the new positions. And this continues. Next one, next one, next one. And now, actually, the forces have reached the convergence criteria here, which I mentioned here. And I think these were the default values. We can, of course, give these in the input if you want a stricter convergence criteria. So you can change those in the input. And then we have this section, which you see now it says something about final. These are the final coordinates. So these are the coordinates that are the end result of the relaxation. Now we see the position of the atoms. We will use the X-10 to visualize this. Now we use the output file, of course, and we had to modify the option from I to O. And again, I reduced the dimensionality. This is just for convenience in how to see the structure. Now you see we have these 4 options. We can take the initial coordinates, so this would be the same as were given in the input file. We can use the latest ones. Actually, they are in this case the optimized coordinates. This is because the calculation has converged. That's because we have this final section around the latest set of coordinates. During the run, one would use this latest one if you want to see the latest one. But actually, we can also have a look at all the intermediate ones also. So we can choose the last one, and we visualize this. And then you get this animation control. And these 6, it says slide. So these are the different geometry relaxation steps. You can also kind of display them as a movie, but now we just look them one by one. So this is, it always starts from the initial geometry. So you remember this was the flat one. We started from that one. So if you click on the arrow, a single arrow to the right, so it says next image. So this was the initial geometry, 1 out of 6 geometries. If you click the next one, or the arrow to the right, so next image, you click on the second one, third one, and so on. And with this rightmost button, you come directly to the last current slide, which is the last one, so 6 out of 6. So this is the 6th geometry, and this is actually the optimized geometry. And what you see is that now the 2 atoms, the carbon atoms, they are no longer on the same plane. And this is what you could also see from the atomic coordinates, the numbers. So they have displaced them vertically. And of course, the hydrogens, they follow the carbons. And what this looks like is, so I just show a bit more of these cells, how this looks like. It's like in the PDF file. So every second pair of these CH atoms is going up, and every second one is going down. Now the question will be, why is this? And I mentioned already something about the chemistry at the beginning. So sp3, if you think of sp3 hybridization, That's of course the tetrahedron. Again, in graphene, you don't have anything above below the plane, and the carbon takes the sp2 hybridization, and it's perfectly fine there. It's a semi-metal. Here we have sp3, so it's like a silicon bulk would be, and so we have somewhat out of plane organization, so that we get a bit closer to the geometry like that would be in a tetrahedron. So around each carbon atom, you have three. Let me see if I can zoom a little bit. So if you take, for example, this, just a second. So if we would take this carbon atom, for example, and look at how it's coordinated. So it has 1, 2, 3 carbons, which are slightly below, and those are those ones by this translation symmetry, which are below the plane, and where the hydrogen is below them. You remember there were 2 carbon atoms in the cell, so one had the carbon up, the other one down, and by these periodic boundary conditions, these are all 3 around this central carbon atom, and then there's 1 hydrogen above. So this gives the central carbon atom this kind of sp3 hybridization. So it's close to the perfect sp3 tetrahedron. And then, of course, if you would look the same for the other carbon, it's just that it's below the plane, but it has the same. It has 3 carbon atoms above the plane, and the hydrogen beneath it. So this would also show up in the electron structure. Now we are not going to look at that. That was not planned for the exercises. But if you remember difference to the input of graphene, now we actually have commented out the occupation. And this is because we know that this is actually a semiconducting system, or is it even an insulating system? The hydrogen atoms, they kind of saturate these carbon atoms, and instead of the graphene, which is a semi-metal, you remember there's the gap closer at the Dirac point, and you saw the density of states. Here actually there would open a gap, but we are not going to analyze the electron structure. If you want, later you can do this. You can plot the density of states and so on. Now, because we are not using the occupations in the outputs, just quickly repeat that. When we saw the K points, the occupation numbers, these are all occupied states. So no unoccupied states are calculated, so we don't get automatically the band gap from this calculation. So you have to do an self-esteem calculation, or otherwise you have to include unoccupied states. So this is if you want later. So now the idea is to do this relaxation if you haven't launched the job yet. So we wait a while, and we hope that everyone has managed to run this example. So if you have not managed, or let's say we give it 2-3 minutes, you try to launch this calculation if you haven't done it, and then you try to look it in the ESPRESSO. And please let us know on the Slack, or well, you can also raise your hand in Zoom if you have any problems, or if you have any questions also. So now it's a couple of minutes. Let's take a couple of minutes, and you can try to accomplish this calculation. So let me see. I try to follow. I don't know. Anyone has a question on?
So if someone want to ask some question, can raise their hand right now.
Yeah. So now it's a good time. If you have any questions, problems here, because this is the first relaxation calculation. If you have any doubts or so, you can ask now. We use a couple of minutes for this.
Yeah.
And then we go to the next exercise. Of course, you can keep asking questions, but I think now it's good time. Either launch the calculation if you haven't done it. If you have any problems, please report us so that we we remain synchronized at the beginning of this session. So, and I think, yeah, Alessandro, you can keep track.
Yeah, I will check.
I mean, I don't. Okay, nothing on the chat of the Zoom. That's always good. Anything on the Slack? So there's a answer. Yeah, thanks, Felice. There was the answer. Felice answered about the ESPRESSO. Like I said, you launch, as usual, we launched the ESPRESSO. And the first question it asks, do you want to reduce the dimensionality? Here we can do it. Initially, actually, you might, I mean, you can keep running the example. I'm just explaining at the meantime for the others if you have already finished. Initially, it might be a good idea to show, maybe I will show here. I mean, we can take the initial. Now I don't reduce the dimensionality. And I show the optimized coordinates. And now we can have a look. And as I mentioned, it's not that interesting to look in this direction, but something I think it was mentioned or discussed to some extent. So the eternal question is, well, I pose it this way. So even if you have, let's say in the real world, you have a two-dimensional system, you have one-dimensional system, you have a cluster, zero-dimensional system, you need to give these lattice vectors in a quantum espresso. And then the question is, how much space do you give? It was discussed whether some people take 6, 7, 8 angstroms maybe. And then the question is it enough? And it was mentioned that, for example, if you have a dipole in your system, it converges much lower. So you might have to go to these algorithms which take a weighted dipole. So everything depends on your system. If you have, for example, ions, like some people have studied the adsorption of ions on graphene. So if you have this kind of, well, it's a very ionized atom, so it creates a strong dipole if it's only above the plane. So then you probably need much more space also. It depends on really on your system, how do you localize the IO electrons and so on. So here, initially, you can have a look and get an idea how close the atoms are. And I will not give any value. So you always have to think what is enough for your system. So you can do the convergence check. So
Arim, there are some questions on the streaming. Maybe we can get some question now. If one geometry does not relax, can we reduce the upscale parameters?
Yes. So you can try to make the kind of the steps, at least initial steps, smaller. So if your structure keeps just taking many BFG steps, and if it looks like the structure is not converging, then you can try, for example, to reduce this upscale parameter. I checked, and I think 100 is actually.
So he's also asking what is the reasonable values for this parameter. I mean,
well, the 100 is the default. I think I checked, so this would not be even needed. But most of the calculations relaxation that I have done, they have converged with this value. Again, it depends on the system. In some kind of systems, you might have better luck. Better luck means that you converge faster. So, like I said, basically always I have managed to get the converged geometry. If it's a global global minimum or local minimum, we cannot say. But BFGS, in most cases, it's converged. And then it's more, this upscale is more how fast it converges. So if you need 10 steps, 20 steps, there are cases where I have needed hundreds of steps, and the default is 50 iterations. In the ion section, you can put the variable to increase this. The other option is to make a restart. So you continue from the previous geometry. What I do sometimes is also I reinitialize the forces and or the history of BFGs. So I just copy the coordinates into a new input file without doing a restart. Because with restarts, if you do a restart in the control section, normally it also restarts with the history of the relaxation. And what I do is just I start from zero. This kind of forgets the history, because I don't know if it was clear. So
okay, so I think some of the tutors actually can also answer in the streaming chat from YouTube, and
also
and
if you
some
have
other tutors maybe can answer the questions on Slack. while you are doing the exercise, so that we can optimize
Yeah.
the question session.
Yeah. So I hope now everyone has finished this exercise. Again, if you didn't.
Okay. Anyway, someone is suggesting to slow a little bit down, so maybe you can.
Okay. So is there someone who has had problems running this example? I mean, just please let us know, so we know that we remain synchronized. Just write on the Slack immediately that I still have a problem, and we can have a look together. Is there anyone?
So one from streaming was was saying that getting an error bad option PWI.
Sorry, that's in the.
Well, I don't know what was the step. I'm writing here in the chat of Zoom.
Zoom. Okay.
No, I just reported it here.
Okay.
From the.
So let me see on Slack, day 3. And well, maybe I will not start to read all the if the answers were satisfying. Ludovic Azzulo, that's the latest one. Is there a way to get a good trade-off between the energy convergence threshold and force convergence threshold? Again, it depends on your system. I'm sorry to say. So, I mean, you could try. In some cases, I might say, okay, I don't care about the energy convergence. I'm only care about the force convergence, or the opposite. So there's no general. I mean, you can say, okay, in most systems, maybe one parameter is 10 times the other one. I think this is what I usually use. I mean, I cannot, I don't have at hand those values. Usually I try to converge a bit stricter than the default ones. And then you will see later during the week, I think, in the phone calculations, you have to relax very, very accurately, because a small error in the optimized atomic positions might lead to very large error in the calculated phonon properties, so phonon frequencies and phonon modes and so on. And just a general comment. I mean, while I hope everyone else is finishing, if you haven't done it already, a very general comment about these threshold criteria, and this is very general also on day 1 and day 2. So everyone at the beginning asks, what is the value for the convergence? And it was given, I think, 1 millirad per atom, but the really tough answer is it always depends. It depends what you want to look at. So if you want to look at the phonon frequencies, it might be that the criterion doesn't hold. You have to go to a stricter convergence in the cutoff energy, in the number of K points and so on. The same is for the forces. There's no general rule. It's unfortunately quite a lot of experience that how accurate do I have to go? Because like I said, for the different quantity, if you just want to relax geometry of, for example, atom, molecule, and surface, it's probably enough quite loose the default values. But if you want to calculate the vibrational frequency of that molecule, then you might have to converge the forces much better. And then, yeah, convergence of the energy and forces is of course related, but there's no direct rule that it's 1 to 1 or 1 to 10 or so. Unfortunately, it's mostly experience. So now I hope everyone has finished the first exercise. I see now there's someone who has been running the next exercise. So that's I will show. So here was this small explanation. There's an image of this system. And then here was the final geometry. So it is so-called buckled structure. So every second atom, there are 2 carbon atoms, 2 hydrogen atoms per cell, and this is then the periodic replicas, what you see in this image. So every second carbon atom is kind of above the initial plane, and every second is below the plane. So this is what we have executed now. So the next exercise is somewhat more. Oops, sorry, I'm confused. Keyboard shortcuts. Sorry. So the next exercise is then to run bits more. Well, let's say a system with a bit more decrease of freedom, and that's studying the adsorption of oxygen. Sorry. Of course, this is an input file. So the next systems we're going to look at, again, I reduced the dimension to here because it's a two-dimensional system. So this is now, in the previous example, we put hydrogen at each carbon atom. And now we are looking at the adsorption of, in principle, isolated oxygen atom on the graphene. And in this case, we have chosen already this supercell. It's mentioned explained in the exercise sheets. So we have chosen 3x3 in both directions, 3x3 unit cells. This is the so-called supercell. So instead of the 2 atoms that we had in the first case, or in the case of pure graphene, now we have 18 atoms. If you would count, you will have 3 times 3 simple unit cells, and then there are 2 atoms per cell. So 2 times 3x3, that gives 18 atoms. And then we have 1 oxygen atom, which is now above one of the carbon. Well, sorry, it's kind of breaching above the plane between 2 carbon atoms. Sorry, I tried to. You see, this is so-called well, epoxy group. So an oxygen with 2 bonds to the hydrogen, kind of creating this triangle carbon-carbon oxygen. And this is a model for the graphene oxides. This would be a long story. So this is one of the groups which is believed that exists in the graphene oxide. So now we took this just as the example for today. So it's adsorption of this oxygen and how it creates this so-called epoxy group on the graphene. And we chose 3x3. Again, it's maybe not enough. This you would have to do a convergence check if you do all the calculation in 3x3. Well, you could even start 2x2, supercell, 3x3, and cell 4x4, and then you would check when your parameters that you want, for example, the adsorption energy of this oxygen, when are they converged with the size of the supercell. So now it would not be converging with respect to of K points, but also the lateral dimension of the supercell. This is what you should do before starting this, because again, the oxygen now it's above the plane, so it will create a dipole. It will be partially charged, of course, it is more electronegative than the carbons, and so on. So it kind of creates a dipole, and it's partially charged even, so it's kind of this 1/r dependence on the distance between the periodic replicas and so on. Again, this we don't do today, but you should do that if you do a real project. You should be kind of sure that these defects or these adsorbates are far away periodically, that you are converged or converged to some criterion. I don't know, some 10 millielectron volt interaction between the periodic replicas. Okay, this is the system. This is the coordinates, and if we have a look in just how the input looks like, it looks pretty similar as before. So again, it's a relaxation calculation. Now we had to multiply the lattice constant in the hexagon case by 3, because we have 3 unit cells, and then at the same time we divide this third cell dimension, which was the C over A, by 3, because the A was multiplied by 3, so we can divide this C over A ratio by 3. So now the distance actually remains the same between the planes. And we have, I mentioned 18 carbon atoms and 1 oxygen atom. And we have 2 types, again, because we have the carbon and the 1 oxygen. And I haven't I mean, I have tried to follow the talk so far, but if I missed this, as a reminder for the cutoff energy, if you have several different kinds of atoms, if you have check the convergence, for example, for carbon, you have checked the convergence for oxygen, then you always have to take the cutoff for the highest ones of those elements. So now we know from experience that the oxygen convergence is lower with respect to cutoff than carbon. So you should choose the cutoff value which makes the oxygen converge. It's just a small side note, but now for the computational efficiency, again, these values might be a bit too low, but you might want to check those in real calculations. So otherwise the input is more or less the same. Now we do use the fraction of occupation numbers or the smearing because we are studying graphene. The oxygen disturbs the electron structure, but as you can imagine, there are 16 atoms of carbon which don't have oxygen just close by. So probably this direct cone, it doesn't survive because we break a little bit the symmetry by absorbing the oxygen, but it will probably remain with the small gap the system, or it might even become metallic. It depends also on the initial geometry. Okay, so the coordinates, now actually we use we give the coordinates in angstroms, not in the crystal coordinates and not in the coordinates with, like in the previous example where we gave the coordinates as a function of the ALAT. Now it would be funny to use the ALAT because from the simple unit cell, you remember we took 3x3 supercells. So we had to multiply this parameter LDM1 by 3, and that changes this ALAT parameter. So we should change the coordinates corresponding if you're using the ALAT coordinates throughout. So now they are giving an absolute coordinates in angstroms, and we have the 18 atoms and the 18 carbon atoms and the 1 oxygen atom. Now there's this remark, yeah, we should actually use 3x3x3, but it's a bit too slow on the virtual machine. So we cheat a bit and we use gamma point only. It's certainly not enough. So yesterday you saw we use 9x1 in the case of graphene. Now that we have a supercell 3x3, you can easily verify. That's also a good exercise of the folding of the K points when you go to supercells, that the corresponding K points would be 3x3x1. And this is what we should be using if we were consistent. But again, to be a bit faster, we use this only the gamma points. Now you can, if you haven't done it already, you can run this example. Sorry. Sorry. I said, if you haven't done it, you can launch the calculation now. And if you have extra time, again, you can have a look at the output. Of course, the beginning is similar. Now it does the self-consistent loop. So, and now you see the system requires more steps for the initial convergence. So here in the case of graphene, the previous example, we need 8 iterations. Now it took 12. And now we actually have the also some unoccupied states, and because of the smearing, the broadening, and the Fermi energy, so one sees that okay, the Fermi energy is between those two values. Again, this is certainly too little on the gamma points, but this is what we can easily reach on these computers. And again, now we have this smearing contribution because we're using the fraction applications. The fourth is, now you see that also we could have checked in the beginning. So because the symmetry is now much lower, there are forces also in the lateral directions. So there are no zeros anymore. So the symmetry doesn't keep any of the forces zero. And then we see, okay, the forces on the oxygen vertically, that's the largest one. These forces, initial forces, they of course depend which kind of initial geometry you have given. So that might be a huge one if you have a very bad starting geometry, or it could be already very small if you manage to start very close to the final or the converged geometry. So the same kind of thing, it shows the first forces. This was the first self-consistent cycle, and then this was the 0th BFGS optimization step. And then the calculation continues. Now we are at step 7. So on my machine, I started it some 2-3 minutes ago. So this indeed, like it was mentioned in one comment on Slack, this example takes a longer time. It takes longer time already because it has more atoms, and the calculation time, if you would have the same kind of atoms, the same cutoff, it converges. Oh, sorry, the computation time scales with the second, third power, in principle, the third power, the number of atoms. So if you now put 3 by 3 supercell, so it will be more or less 9. Sorry, there were 4 atoms in the first case. Now we have 18, so let's say 4 times more atoms. So if we would have the same K bonds, this would be 4 to the third, roughly. So 100 times slower. Now we only use gamma point, but because we have more atoms, in principle, the calculation is already, because of that, it's heavier. And we are, again, as you saw in the beginning, we are only using one processor. So we are following the steps of the self-consistency. Again, we can check the previous one. So 12 steps, and it seems that, okay, between the old and the new geometry, the energy, total energy of the system is changing already very little. So we hope that soon we will be converged. Again, already 14 steps, but I think the forces, well, they are reducing. And usually this BFGS, it's at the beginning, it needs more steps because it's further away from, it needs more steps at the beginning to reduce the forces, and then it starts to learn about the system. Like said, like Pietro said in the morning, it starts to learn how the Hessian more or less looks like, and then it can use this information, and the forces, they reduce then faster toward the end of the calculation. This is the, sorry, present values of the forces. Again, going down and down and down, but there's still some forces which are too large for the convergence criterion. So in the meantime, while the calculation is running, just to make sure, has everyone managed to launch this calculation? Either it has converged or not, but do you have this calculation either running or it's finished? So please, again, give a quick comment on the Zoom or on the Slack, so that we know that there are no problems running this example. And I mean, it's not, okay, now it just converged. It needed 20 relaxation steps. Again, this depends on your system. It depends on the initial geometry, how far it is from the final one, and so on. So we can have a look on the structure again. Well, I go first to 2-dimensional reduction of the visualization. We can take again an animation if you want, or I go directly to the optimized one. So this is also the latest one. So the last 24th step. And this is now the final optimized geometry. And as it would be expected, well, far away from the central oxygen, the planarity is more or less kept. So you see that more or less the carbons are still in the same plane, but then this epoxy group has somewhat lifted out of the plane. Maybe also the second neighbors, but less. So this is, again, it's kind of clear that the carbon, it doesn't want to keep the planar hybridization, so it kind of lifts a little bit to get closer to the sp3, and then probably there are the dangling bonds on the other side. But this is expected that two carbons would also lift with the oxygen. And now, if you want, you could have a look, for example, in the bond lengths between the carbon and the oxygen. So if you choose the carbon, the oxygen, now the bond length is 1.5 angstroms. So that's a very typical bond length. And again, this is in this case of the epoxy group. So by internal symmetry, that the other bond length should be more or less the same. And the carbon-carbon distance is 1.45. We can check, we don't have the initial value, but more or less far away, it's a bit smaller. Of course, because the coordination here far away, or in the perfect graphene, it's the sp2. So the bond lengths are a bit shorter to have this hybridization and kind of the electron density around the carbon atoms. And here it somewhat increased the bond length because there's the fourth bond to the oxygen now. So that's why the carbon-carbon bond length is a bit shorter. Sorry, it's a bit longer than in the carbon-carbon bonds without the oxygen. So this is quickly this example. Has everyone finished this by now? So I see there are some questions also about the chemistry. Yeah, Tony has answered. So in principle, now it's a good note from Josef Hannis. You saw that in the first case we adsorbed the. Now I have some problems on my machine. Some problem on my machine. Can you still hear me?
Yes, absolutely. Yes.
Yeah, because I cannot change between the desktops on my computer anymore. Something has frozen on my machine, or it's just very, very slow. So I cannot go back to the virtual machine anymore. Okay, there we go. Sorry. A good remark. So the first example, let's say the 0th example, that was the graphene, which you did also yesterday. It is planar. There's no need for this dipole correction. There's no dipole in the vertical direction. As Tony explained yesterday, if you have two different kind of surfaces, you will have a different potential, or the asymptotic of the potential, and in principle you need this type of correction. And in the first example of this morning, the graphene, we put the hydrogen on both carbon atoms, and because of the symmetry, there's no dipole across this slab. But today in this example, indeed there's a dipole. I mentioned that this oxygen gets polarized and so on. So in the really good calculations, one would indeed put the dipole. So one would put the dipole correction so that it's in between the two layers, so that it doesn't affect this kind of discontinuity or a step in the potential which is added in the dipole field. It would not affect directly the electron structure of this structure. So that's why we need to have enough vacuum also that we can put this potential in the vacuum between the planes. And this is again what should be checked. Well, Tony showed that example yesterday. We saw that there was enough vacuum so that the potential gets really flat, and then there's this kind of step discontinuity, and then it goes to the other side of the back side of the slab, and then you have a different value of the potential. So indeed, here one should use the dipole field to make a very good calculation, a good note. Any other comments, questions about this example? Okay, so we continue. I don't know if someone has a step story further.
And if you have the chance and you can read the streaming, you might get some question there. I don't know.
Yeah. It's again interesting to read. Read which question has already been answered. It's not in threads. I see that Matic,
Yes,
they are already answering. So it's a bit.
Okay, no worries, no worries.
So, any questions now? I mean, you can also raise the hand. We can stop here if anyone has an urgent question until now. If there's nothing, then we go to next step. So we will go to the case where we also relax the lattice vectors. To be honest, also in the first case, yeah, we should have relaxed. In almost all cases, we should relax the lattice constants. I mean, it's also there's discussion about strain and so on. So we can also relax with an external strain. So there are a few cases where one doesn't need to relax at the beginning the lattice constants or the lattice vectors. So here, as a reminder, well, sorry, now we go to a case which looks very similar in the lattices. So that's the HCP structure of bulk zinc. So that's an elementary crystal, and zinc crystallizes in the HCP structure. And HCP is exactly what we used before. So that's the IPREV4. You see here the value which we are going to use, it's IPREV4. But now it's different in the sense that now the C value, it's not the 2D material, it's bulk material. So in the third direction, there's the C, and now the C is really significant. We don't just choose it so that we isolate the layers from each other, but in the HCP crystal, each of the layers is interacting also in this third direction. So now the C is really a physical value, and that's, you will see then that in the databases structures, C files, you will see a value for C also. And otherwise, it's quite similar. So the lattice vectors are similar. Like I said, we will be using the IPREV4, and there are the two independent variables, A and C. Now we optimize them both. And there are two ways, two rough ways how to do this optimization. One is the manual way, which is noted here, and that's calculating the potential energy surface. So we will calculate several values of A, calculate several values of C, and then we get the two-dimensional plot. And the optimal values are there where the energy is the lowest. So we will, with this algorithm, if we just calculate the grid, we will probably not hit that value, but we could, for example, interpolate or find a more intellectual way of choosing, of evaluating the exact points where the energy is minimum, and those are the values of A and C that we would have using the approximations in our calculation. So again, the cutoff energy, the K points, and most important, the exchange correlation function. Again, notes here what we will get as lattice vectors, they don't correspond to the experiment. And even if, in most cases, even if you would have most converged cutoff energy, most converged K point sets, most converged or best possible pseudo potential, or even the hard potential, the Coulomb 1 or R potential, you will not get the experimental lattice constant. And often these are not the values that you want to get, because there's the exchange correlation approximation. So you should get the values which are best converged with respect to your exchange correlation functional. And if it's away from the experiments, well, that's because of the approximation. But you should not compare, oh, I have better correspondence or agreement with the experimental values if I, for example, use a lower cutoff. No, that's I would call cheating. You should just converge everything, and then those are the values. If you can exclude all the other sources of error, tough luck. That's just correspondence to the experiment. And usually, well, we are using, in most of these cases, we are using a GGA, and it has been maybe seen already. Usually we are more or less 1% larger than the experimental lattice constant. And I would say 1% is not too bad. And then that's the value which traditionally one would use. There are cases when one uses actually the experimental lattice constant for the real calculations applications. But here we now try to determine the optimal A and C, these values by two ways. The first one is the manual way, and this is just, as I mentioned, sampling the values of A and C, hopefully so that in both directions, the final optimum value will be inside this two-dimensional grid, and preferably more or less at the center. And there's already a ready script, and this we can launch in a while. And this is the PWTK script. You have already experience on PWTK from the previous days. So this is a way how to calculate. You can calculate that on your local machine. It takes a couple of minutes, or we can use the remote computing. We will now go to the remote computing. If you haven't studied that yet, we will start that with this example. And the second way is this variable cell relaxation. So that's just almost the same as the calculations before. So when we did the relaxation of the atomic coordinates only, but now we change from relaxation to variable cell relaxation. So the calculation method changed it from relax to VC relax. And now we have to include the cell name list, even if it's empty. And I will just show the so the first example. So the first way to calculate was this two-dimensional potential on the surface. There we use the SCF. Actually, we could even use the relax, but there's nothing to relax. Due to high symmetry, there's nothing to relax. The coordinates will have zero forces by the symmetry. They will be stressed, but if you to relax or SCF calculation, it would give you the same result because the forces will be converged in the first step. But let's have a look in the inputs with the relaxation of the lattice vectors. So again, the calculation method has been changed to VC relax, and we have included the cell name list. That's basically all. One more side remark, which has probably been made, but to make sure that you remember it. Now we are calculating the stress tensor. So the stress tensor is needed for the VC relax. So Pietro explained that this morning. So this is the derivative of total energy with respect to changes in the lattice vectors. And this is a higher order derivative. If the forces were already derivative, so this is a higher order derivative, and this actually converges slower with respect to the cutoff energy than the forces. So the easiest to converge with the cutoff, if you increase the cutoff, is the total energy. The next one would be the forces, and the third one, unfortunately, is the stress tensor. So usually you have to go to a higher cutoff energy if you want to use the VC relax. And again, this is then you have to test the convergence. We don't have enough time to explain that fully, but then Pietro already mentioned that, okay, the last step will be done with the new basis set that was calculated or re-initialized with the lattice vectors of the otherwise converged geometry. So you will see that in a while. So this is the relaxation using the variable cell. And sorry, Tone, are you?
Yes. Yes.
So shall we launch this now on the remote cluster?
Yeah, we can try.
Yeah, so this will be, if you haven't tried to launch anything, so here there are these two steps, the manual step, which is the PWTK script, and then there's this step where you can directly run PWX, with this input. And both of these can be run on the remote cluster. So let's try our luck. Now, if you don't remember anything from the day 0, or if you joined a bit later, but let's hope everyone has the remote access. We will now be checking that on the fly, if yes, if not. So at the beginning, after the introduction slides, there were the 2 short introductions to the execution remotely. So the first one is the remote execution of the executables. So here it's a PW.X, and this is now for the input using the VC relax, because that's a ready input for the PW.X. And if you want to, or when you want to run the PWTK, this zinc-scan.pwtk, you can run that remotely using the remote PWTK command. So how you run those, it's just like before, but you don't provide any output. That's not necessary because this output will be created on a remote machine. So for single input file, you would run remote MPI run, then the executable, and now you have to use the -in option, and then the input file. So in a while you will see how this is done in practice. So this is a running MPI run. The second one is remote PWTK, and then the name of script. And then in the output, you will see in a while, in the output you will see, okay, it will be launched on the remote cluster. On the next page, then there are some, well, if you have other kind of script, you can use also the remote dispatch, but we are not going to use it now. The very important point that Tone has mentioned me is that on some of the clusters, I don't give any names here, but there's a problem with the file system, or problem. It's tuned so that you should better not touch any of the files, not even look at the output, not even copy them before the job has finished. So we ask you, once you have launched your job with this remote MPI run or remote PWTK, you use the remote SQ commands, and you can launch it as many times as needed, and you only go to the next step, so copying the output file. So that's actually on the 3rd page. You only do this after you have seen that your job has finished. These jobs will probably not take very long. I don't remember, half a minute or so maximum. So they will be quite fast. The next example will take, I think, something like 2 minutes. And please don't try to copy any of the files. Don't log in on the cluster during that time. This might cause some damage to the files. So just be patient. You can have, once you have launched a job, for example, you can look at the input file using ESPRESSO, and then every now and then you check the remote SQ. If you still have this kind of line, it says that your job is here, it's running, because it's R, and once it has disappeared, your job has finished, and then you can copy the data. So please remember this then. Be patient, execute the remote SQ until your job has finished. It could be that if you make a mistake at the beginning, then actually the job it takes us a fraction of a second on the cluster, and then it vanishes immediately. So even then, what you will do, you can copy, well, all the output file, or even better, you just use the command rsync _from_HPC space and the period, the dot. This will copy all the files from the cluster to their current directory. So in short, you either execute the remote MPI run or remote PWTK with the corresponding options, and then you check your SQ or the queue job if it's still in the queue. Once it has come from the queue, you copy all the files. And I think at this moment, at least, there's no need to copy the files explicitly. So this is done automatically. So please don't execute today the HPC async HPC. This is for your convenience. for later, and we don't need the remote dispatch today, I think. So let's try that. So we come to the zinc example. Sorry, I went a bit too far. So the zinc example, so the manual way. Let's try the manual way first. So that's a PWTK script. Sorry. So there's this zinc file. So let's try remote PWTK zinc scan PWTK. And we hope for the best that it's working now. Okay, that's just the output. It says something, okay, it's submitted the files to the cluster. You don't need to care about this. And then it says submitting the job. And it says it's using, well, actually not process, but 20 cores. And that's probably too much for this example, but you will see that the next example will be harder. It's better to use those 20 cores. Okay, we check 30 seconds execution time. So it's running because there's R under the status. And it has been running 30 seconds. Now it looks like the output is hanging, but just press enter. It's because the job went, the SQ job went on the background. So you just press this command and you can press enter. So it seems that everything is fine. It's running. It's 1 minute. It's still running. Still running. At this point, maybe you can report if you have any problems executing this. I mean, the other command so this was this manual way, and I think well, maybe it's better to wait until this has finished when we launch the other job. So it's 1.5 minutes now. Then there's this other job we will be launching in a while. If you have finished this first step, and if you have a look at the output, you can already go and you can try out. Sorry, again, I'm almost forgot. So the other way was this relaxation with the variable cell. So this is now executing directly with MPI run, the executable pw.x, and the input file is this zinc with VC relax. This you can submit. I prefer that you submit it only when. Sorry, I didn't do this. I just put this so that I remember. So let's check the queue. It's still running. It's taking more time than I remember. But in the meantime, has everyone managed to launch either the MPI run job or this PWTK job remotely? So please raise your hands in Zoom. Please write on the Slack. I mean, I see also I'm following the stream, but I think yeah, there are interesting questions about the van der Waals forces, and I think they will come, the van der Waals functionals, and this will come later during the school. So now we are just using GT8 to keep things simple, but this is certainly a big issue in this, in particular when with this rise of the 2D materials, so between the layers, adsorbates and so on, often, or adsorbates on surfaces and so on, and you have often the weak van der Waals forces. So anyone has trouble? Okay, I still quickly check on Argo. So and then one important note.
So I start to see a few jobs on the HPC cluster, so that's cool.
Yeah, good.
Means the configuration should be fine. So if you have problems, you can either write on the cluster HPC ICTP or even here. I mean, we can join some breakout room if you have some help.
But I think quite soon I will continue with the example. So if you're in the breakout room, then you might miss the following explanations, but well, your tutor can help you further than, or you just follow the PDF file. So I just want to note, I tell it to everyone because it was a problem. I saw it this morning, or someone had asked already this morning, and now there's during the exercises. So these remote commands you run on the virtual machine, not on the HPC cluster. So the idea here was to simplify your life. You don't have to log on the cluster. This, of course, is not the real life of a computation scientist. You probably have to fight how do I log in and so on. But we try to make everything as smooth and simple so that we don't lose time connecting to the cluster and so on. The idea is that you run all these commands from your virtual machine, or if you copied all the data on your laptop or some other machine, but you don't log in to these 3 clusters to execute these commands. If no one reports any other problem now, so I suppose, I hope everyone has done the calculation. So this was for the 2D sampling, the manual way. And now I copy all the data. So I use this rsync _from_HPC and period. So that copies all the files, at least it should. Indeed, we get lots of output files. So we get for each combination of the A and C, we get the input and output file. So there are many output files. And you see already the energies, actually, they have been collected in one of the files. So that's also done on the cluster at the end of this job automatically. And that submission scripts, there's the output from the queuing system, but we are not going to look at those. So now this was all copied. I see it copies a little bit too much. I see that it has all written the references, if I'm not wrong. That was not the idea, but let's see. So here, as you have seen already in the previous days, you will have some ready prepared files. So this is a GNU file, and this file directly plots. It uses the values which were gained on the cluster, and it plots them here with the GNU plot. So you can just take GNU plot. There are lots of these options. We are not going to go through them, but this will show you this 2-dimensional potential surface. So you see, you have this A value of the lattice constant. This was the lateral lattice constant in the hexagonal cell, and on the other axis you have the C. And now in this contour and contour with the lines and the colors, you see the representation, and you see that the lowest energy, I mean, that has been normalized to 0, so that's the minimum, so that's the most blue point. So it's somewhere here, 2.61 for A and 5.27 maybe for the C. So this would be very roughly with the eye looking at this output and concluding the optimal lattice constants A and C from this calculation. So this is what you get. This you can have a look then with the GNU plot. In the meantime, we can execute. Actually, I wrote it already. I mean, this is all in the files, the README files also. If you want, then well, now it's very crowded. This, but you have the README. Well, now it's somewhere in between. There's the README MD, so you can have the exact commands there. So we can launch the remote MPI run for this other job also. So it was remote MPI run, then the executable dash in and the input file, and you don't redirect the output. Otherwise, it's like you will be running interactively on a cluster. So the remote is just this complicated script which launches the job and does all these steps for you. So we try to launch that, and let's see if I'm lucky. So again, it says the job was launched on the remote cluster using 20 cores. So 20 has been chosen actually because I think this is the number of cores per node on that. Well, on let's say on all the clusters, it's a kind of optimal value. And we can check the status of the job. So now it's running since 24 seconds. And now while it's running, you can, for example, look at the potential surface and so on. Does anyone have problems so far? Everyone is able to run MPI run remotely, PWTK remotely. Everyone is happy. Everyone gave up.
The only thing I think that we could now close the streaming session if you agree.
Okay.
So I would I would thank, I don't know, look if there are any left questions. Otherwise, we'll thank the participation on streaming. I think we can close the streaming and the registration as well. And we can stay available for the ones that needs help in here.
Yeah. So then the rest of the exercises you will see.
Hello?
Yeah, Ivan, isn't it half an hour more for the streaming?
Yes, but we stay here, but we close the registration and the streaming. We don't need to register ourselves that we chat one another.
Okay, but there are still examples.
We leave the Zoom open, but I don't know. What do you think?
But I think that Ari has still something,
there are still some exercises to explain. So.
Okay, perfect. No, sorry. I thought we were just left to the exercises.
No. Now I thought we take some time because.
Excuse me. Please go ahead.
No problem. No, we are going a bit slower than initially we had planned, but I think it's good, like you said, that we try to slow down. So we hope that everyone has managed to run remotely. So
someone has problem with remote access.
Okay.
Maybe one can check.
Is that on
Zoom?
On Zoom?
Amal Aldara.
Yeah, I told to Amal to join the breakout room. If he can join the Mondal breakout room, I will be able to.
Okay. Yeah.
To help him.
Yeah. You can also invite this person.
Yes.
Is it Amal who has problem? If anyone has problem, please report now. You can also write quickly on the Zoom or Slack chat, and then we can use these checkout rooms. So someone will invite you, or you get an invitation that you can join there if you have any trouble. So in the meantime, well, later if you now in the breakout room, well, you don't hear me anymore if you're in the breakout room, but if you go to the breakout room, you of course have these slides, and you can ask us later how it continues. But I think it's all clear. You continue, and if you have any questions afterwards, then we will have the Slack also later during this week. If you have questions related to this day, we are there to help you. Okay, so in the meantime, the job had finished. I think it took something like 2 minutes. So this VC relax. So I will quickly explain the aspects. So now there's much less output because there was only one job. There was no loops. Sorry, now I made a mistake. Using the wrong keyboard shortcuts. I hope we are back to my. Well, now I see the resolution is again much higher. I try to go to lower resolution, so it's bigger fonts and so on. It's this one. Yeah, sorry, this is my mistake. Well, sorry, it's still too high.
Ari, you
Yeah.
can leave default, but then you set up the resolution in the virtual box.
Yeah. No, because I managed to do it this morning. Just now, for some reason, it always wants to go back to the high resolution.
No, but you are trying now to set the resolution within the virtual machine.
Yeah, I did it this morning, and I think it worked fine. But sorry, I tried once again. Because then, yeah, I saw that it was okay for my screen. Okay, yeah, sorry, I took the wrong one. No, it again adapts to high resolution. Sorry, just I don't know why it goes back to this. Because I do the resizing of the screen and it goes back. It keeps on. So I try not to do it. Well, I try to do it now. Sorry for that. Yeah, I try to stay at this size.
Ari,
Yeah.
you are now trying to set the resolution within the virtual machine.
Yeah, I know.
Better if you do it from the virtual box.
Yeah, I don't know if it's good time now, but display. I see. I think I try to survive. So, or we'll do it later when the people might be waiting for some. So I hope now. I see the width is not okay, but I hope you can still read my font at this moment. So I did the copy, and I think now it's gone. I just check. Well, so now we visualize these outputs that we got from the remote cluster. So this was the VC relax calculation, and this is the output. So now we don't reduce dimensionality because this is actually a really deep three-dimensional system. I only show the final geometry. It's not very interesting because it actually only changes the lattice constants. So this is the HCP crystal. Not very interesting as such. And as I mentioned, the symmetry is so high that there are no internal degrees of freedom. So let's have a look on the, just reading a little bit the output file. And again, how many steps you need, that depends on the initial geometry, how far it's from the final value, the final lattice constant and the geometry. So I just mentioned here at the beginning of the outputs, they are the crystal axis in Cartesian coordinates in units of ALAT, because this is what is interesting later in the output. So otherwise the output is the same, it just repeats those. Then it does the first self-consistent loop. It shows the eigenvalues at the different k points. So now we are not only at the gamma points, we had quite many. Sorry. Then we had the forces, and no surprise, the symmetry is so high that all the forces are zero. So there's no internal degree of freedom in the coordinates to optimize. But the lattice constants, they need to be optimized. And now we see the value of the stress tensor. So you can let it print also if you don't do VC relax. There's a value input variable in the control section. You can check it up in the documentation. As again, in the browser, you can click on the input variable, so the description of the inputs for PWTK. But here it's automatically printed because we are doing the VC relax calculation. And it shows the value of the stress tensor. Actually, it shows here it already shows the isotropic one, so that's the trace, and that already gives you an idea. If it's a very large one, like here, this value is in kilobar. So here, the stress tensor on the left, sorry, I cannot show, but these values, well, by symmetry, most of them, the non-diagonal ones, they are zero, but the diagonal ones, they are in Rydberg by Bohr to the cube. So this is, you can imagine, this is the energy or change in energy when you change the volume. So that's why it's Bohr cubed or the other unit for the length cube. On the right, you have the same values in kilobars. If you want to think in other units of pressure, you can do the conversion. So, but here is the value, like I said, this is the average value, the trace divided by 3 of the diagonal. And this gives an idea. If this is a large one, you probably have a large stress still, and the calculation will continue. Now, again, we do BFGS on the coordinates. There's nothing to optimize. And we do it also BFGS by default on the lattice. So it looks almost the same. There's just a pressure tensor. But what does change then? The code does not only show the new coordinates; it also shows the cell parameters. And I mentioned initially it shows the initial values in the units of ALAT. Now it does the same in units of ALAT, which is this one. And the first one, I think in all cases, it starts from 1. It's 1.0000, no matter which system, because these are in units of ALAT, and ALAT is always this first. So you have to multiply all these values by the ALAT to get the actual lattice constants. And again, ALAT here, it's in atomic Bohr units. It's not in Ångström, no matter what you gave in the input. Now we see that the value here, it has changed a little bit from 1. So it's about 3% larger. So the lattice laterally has expanded about 3.4%. I don't remember the value in the third direction, but it also has changed. Okay, so this was after the first step. And we saw the pressure is about 185 or 186 kilobar. Oops. And now I search for this. So after the second step, now we had 60 kilobar. So that's again the average of the diagonal. So it has reduced. And again, we have new values for the lattice vectors here and the new atomic positions. The new atomic positions, they are very boring because they are optimized in the crystal lattice coordinates, which was given in the input. So they are relative with the lattice constant. This is what we want here, because the coordinates will be always this. Again, the forces were always 0 because of the symmetry, so these won't change. If you would want to have the coordinates in angstroms, for example, in Ångström, then you would have to multiply these with the lattice vectors, and the lattice vectors have been changed during the relaxation. Okay, we go to the next steps. Again, the value reuses, now it goes negative, so you might have gone a bit to the other side, but eventually we hope now it's the next steps, it's reducing again. Now it's small, and this is now the final calculation, the last step. And so this is now what it gives as the final. Oh, sorry, I went one too far. This is already this extra relaxation that Pietro mentioned this morning. So we had to go to the second last one. Okay, here we are. Sorry for that. So this is the last iteration during the relaxation. And now you see that the value is, well, it's slightly negative, it doesn't matter, but it's very close to 0. And this is considered converged. So now we have converged both the coordinates, or the forces on the atoms, and the lattice vectors. Well, on the forces in this example, it was very boring because it was only, they were always 0 because of the symmetry. But otherwise, the calculation has converged also with respect to the stress tensor. And now we have, again, this final section in the output. So here you see the lattice vector. In the hexagon case, laterally, it has expanded by 3.35%. And this is probably due to the GGA. Well, could be also if the cutoff number of K points is not converged, but those you can always increase. But at the end, you will see that you have some difference with respect to experimental values. And well, main part of that is to the exchange correlation. It could be that the experiments stay also at finite temperature. If you are lucky, you find the values which have been extrapolated to 0K. And they are the nuclear quantum effects, 0-point effects, and so on. But I would say normally you will have 1-2%, two large lattice vectors, lattice constants, if you use the GGA in normal materials, not the van der Waals cases and so on. So these are the final values, and this is the final result from the calculation. And now this one we could use. So the ALAT was 4.80, and the lateral, I only take the lateral value. So now use a calculator. So we had 4.80, and then we have times 1.033 something. So this is the final lattice constants from the calculation. And then if you want to get to angstrom, this would be more or less 2.62. So this would be the lateral lattice constant, the final value in angstrom. And if you remember, the manual way, I roughly said from the screen 2.61. So if one would do it more carefully with more time, you would see that these should be pretty close to each other. And the better you are converged with the cutoff and the K points, the closer you are with it by these two ways. The normally one is, I must admit, usually one is lazy, one uses one method or the other. There are also other ways to do it, but you should at the end get the same result. So if you do it the manual way, the two-dimensional, here we have two-dimensional scanning of the total energy, or if you do the VC relax. Then if you will have more complicated examples where you have more than two lattice vectors, then usually you have even different angles. Now we had this 120 degrees in the hexagonal cell, but then 90 degrees, so direct angle between the lateral and the vertical. So there were only the A and C. But if you have a more complicated ones, I must admit that most people, me included, would use the VC relax way. But please be careful. There's this issue with the convergence with the cutoff energy and this finite base set that was explained by Pietro. So there are tricks and, well, tricks or ways how to try to minimize the error due to this. But we don't have time to go into this today. If you have any problems, any questions? So those of you, if you want, at this point, you can go to the next example. This is just a small modification of the previous one. So this again, you would probably want to launch this remotely. So you see, this is a direct input file for the PW.X. So you would use remote MPI run if you want to execute this. This will take again some minutes to launch. And the difference here is that now all the forces with respect to the coordinates, they are not zero by symmetry. In this case, so this is a crystal of urea. So it's actually a molecular crystal. So urea is a small molecule, and it has its bond length and so on. So these all depend on also on the interaction between the molecules. So now we would, in this example, you will see that you will not only relax the lattice vectors and the atomic coordinates, the forces are zero on the atomic coordinates. This is not the case here. So you will be relaxing both at the same time in this example. But I suggest that we carry on further. We are running soon out of time. And I will now quickly explain the last exercises, and then you will independently continue those. Independently, we will have the tutors, and me, Tone, will be around, not only until, well, it should end in 15 minutes anyway, but we'll be available sometime later. If you have any questions, of course, we are available on Slack. So now I will use the rest of my time, I think 15 minutes, trying to explain what is left in the exercises. But if you don't want to listen to me, if you are confident, you can do it without some explanations. You can carry those. Otherwise, it's time that it's called you sit on your hands and don't use the keyboard. That's a way to say that you don't try to execute all the commands at the same time and trying to listen. But if you try to listen, I will try to quickly explain the rest of the exercises. And then again, we have the chats and we had the breakout rooms if you have any problems or any questions. So this is the example 2. Example 3 is an example on the notch elastic band. This was what Tone explained this morning. And this is the first one is very simple example. I will not go into details. It's very funny that even if you have only a few hydrogen atoms, this could be very difficult for the DFT to be converged. That's because of some issues. We don't have time to go. It sounds like a very simple system, but also if you just this, it will be horrible to treat with any of the exchange correlation functionals. But now we just believe that everything works. So we will use DFT to get the forces. Everything is fine. In the first case, example 1A of the NEB, we start the calculation using no intermediate image. I mean, Tony explained you can use these intermediate images. And here we just start, and I will show you already some slides later, you will see. So we have the initial state, the first image, which is that the two hydrogens are close to each other, and then there's the third hydrogen a bit further away. The last one is just we have exchanged the central hydrogen, so it's very easy to imagine. They are all on a line in this case. Actually, it's a there's a one could say only it's a one-dimensional system, or if you think it's two distances, but if you consider the difference of the two distances, then you will have only one-dimensional potential surface. But anyway, this is the first image. This is the final one. The difference is that you have shifted the central hydrogen from one side to the other one. And now we want to calculate the energy barrier for this reaction. And the default method, if you don't use these intermediate images, it's just one dozen linear interpolation. So this would be the central image. Depends on how many images you will be using. You will have some intermediate images between the first image and the central one, and then the last image and the central one. So basically, you just interpolate between the first and the last one, and this image in the middle is just a consequence of this linear interpolation. So the more points you have, of course, little by little, the hydrogen is shifted, because again, linear interpolation is done numerically. There's no DFT, nothing. It just takes the initial coordinates, the last coordinates, and this is linear interpolation. And Tony mentioned, please don't swap the atoms or anything, otherwise you will get horrible, well, I won't call it anymore chemistry, but some very difficult geometry. So here, because the first image, final or last image, you have the same coordinates for the first and the last hydrogens, they will remain the same in this linear interpolation. So only the central hydrogen is shifted. So this is the first example, example 1A. Again, on the examples, the inputs, and so on, they are given. And here we use 7 images. And what you will get is then, once you run the examples and GNU plot, you will get a plot like this, where you get the reaction barrier. So you go from the initial state 0 to the final state. It's just the reaction coordinate is given in arbitrary units. Actually, it's a scaled units. So you see it goes from 0 to 1, and it's symmetric. And we saw it already. This, if you have the H2 first on the left, on the right, it's the same. So that's also why the potential surface will look symmetric. The second one is a kind of numerical exercise. This is now using the intermediate image. If you use this chemical intuition, we can imagine, okay, and the real reactions, the last hydrogens, they don't want to stay where they are all the time. And this is the initial configuration that you will get using just this linear interpolation. But probably in the intermediate one, you will have something like, well, a symmetric molecule when the three hydrogens are closer to each other. So again, the initial, or the first hydrogen, it has gone a bit further with the central hydrogen, and the hydrogen initial on the right has come a bit closer to form this kind of image. And so this you can insert using this intermediate image, and then you give the system or the computer code kind of more information than just the linear interpolation. And sometimes the linear interpolation doesn't even work. You might have a reaction. For example, you have an atom which goes from my one hand to the other one, but there's an atom in the middle, and you want to see the diffusion above it. Now, if you take the linear interpolation, you will kind of shoot. You have a direct line in the linear interpolation, and the two atoms would come very, very close. So in this case, the linear interpolation would not work, and you have to go to something like intermediate image. So it depends again on your system. You might be forced to use this. In this case, you can calculate also using this linear interpolation. And the idea here is to look at the difference. Well, you should get the same potential in the surface at the end. Sorry, here independently, but it says that the computation is more efficient to give this intermediate image. So you will check how many steps you needed to get to the converged potential in the surface. This is the idea of the first exercise. Then the second one is again a net calculation, and again here we will use the intermediate image. The physical system is H2 dissociation on a metallic surface, the so-called 100 direction of the aluminium surface. Aluminium, you have seen the example here before. In the earlier days, it's a FCC metal, and then we cut the surface along the 100 direction. And now we want to see what is the energy barrier for the H2 dissociation. Is there a barrier, and how high is it? And what is the initial state? Well, that's H2 in the vacuum. And then it would slowly approach. And what would happen chemically? Well, you will see also in the movie or in the visualization when you visualize the structure in the intermediates. And the final state, dissociation, is that there are two hydrogens which are on the surface. So depending on the reaction, they might dissociate and remain quite close. It could be that initially they already dissociate and go further away. What usually happens is that they will stay quite close, but then also due to the diffusion, then the other atom will diffuse further away from the initial one. This is now quite simple. You will see it's only 2 layers. Also laterally, the cell is too small. This was just to keep the calculation reasonably fast. So again, this would not be sufficient for a real scientific project, but you will see the idea. You will get the idea from this example. And then there's the script PWTK, and then the commands how to run this example also remotely. And then you will plot this potential and surface again, and you can visualize this intermediate ones. So you will see what happens chemically. And then later, if you want to continue, we can discuss also how it looks like. And if you have questions, what happens? Why does it look like this? We can do this later. But idea is now I just will give you a quick glimpse what you are going to do, and then you execute them. And then if you have questions later, you will have us probably explaining it. Then there's actually now we have a short tutorial on PWTK. Thanks a lot to Tone for contributing this wonderful software. And we will use it further also the more complicated quantities. You have done already this convergence test and so on using this very nice way of creating loops inside PWTK scripts. We will use that also for other kind of analysis, which would be again more complicated without the PWTK. And the first example is just, well, equation of state. We will be looking how to calculate the equation of state of material. The second one will be the adsorption of oxygen on aluminium 111. So this is very similar to the previous one. Sorry. So this was the one 0, 0 direction of the surface, the 1, 1, 1 would be a different orientation of the surface. And we will be looking the potential energy surface of oxygen at different places of this oxygen laterally on the aluminium 111 surface. And then the third one, this is more elaborate, and we have already written in the slides. This is left as a homework. If you want, you can continue. I think the reservation will continue, so you can continue during this this session. Also, if you have questions, there will be actually a very nice chemistry going on. This CO adsorption on metal surface is chemically very interesting. It has been discussed a lot, and that there are lots of works on this. So it's very intuitive also chemically. And for those of you who want to look it up, so it's the so-called Bleiholder model, which was initially proposed to explain the chemistry of the CO adsorption on surfaces. If you want to read something more boring, you can read my thesis. This was one of the topics I was studying during my PhD thesis, adsorption of CO on, I think it was a ruthenium 0001 surface. So that's why also I know this, but actually the example doesn't come from me. It comes from the previous edition of school. So these are the three examples here in the final section. So there's some explanation of PWTK, but then there will be the explanation how you would run this calculation of the bulk lattice constant of rhodium in this case, because you saw the third example is rhodium surface, rhodium 100. And this is now we will be fitting the lattice constant, and you will get while using different analytical forms of the potential energy as a function of the volume. So this is what you will get in the outputs. Then the second example was this oxygen and aluminium. Again, here we are going to do a loop using PWTK where this oxygen goes along the surface. And here, maybe I mentioned here, it came already during the previous example. If it was not mentioned already, how you can fix atomic coordinates during the relaxation. And also, I think if it was not mentioned, you can fix during the optimization of the lattice vectors, you can, for example, fix one of the lattice vectors, two of the lattice vectors. There are different ways. And you can imagine if you want to optimize, for example, the lattice vector of graphene. So you know it's only a one sheet. So not graphite, but graphene, one sheet. And then we had this vacuum between the layers. And there, even if you would take a large amount of vacuum in the vertical direction to separate the sheets, there is always some residual pressure calculated by PWTK. And then it would start to modify the amount of vacuum. I don't remember if it would finally, it would try to, well, bring the layers together. So there it's actually preferable to keep the layers apart. And there are options in the relaxation. It's so-called the cell do-free option. You can look that up. That's in the cell section in the input for PWTK. I just mentioned it here because I think it didn't come before. And the same here, I just show, here we insert the oxygen atom. And well, I show this. So this is then what you will get actually as a output. So you will get the potential energy of the oxygen when it's laterally at different positions along this aluminium 111 surface. This is what you will get as an output. But we want to have the height of the oxygen relaxed during this calculation. And how we can achieve this is that we fix laterally the coordinates, and these are not the input for PWTK, this is PWTK, but it's the same thing. So you give the three coordinates, no matter in which units, and then you can put three values, which are either 0 or 1. And 0 means you fix this coordinate. 1 means you relax this coordinate. So these are three integers. You can leave them out. This means relax all those. If you specify, I think if you specify one of them, you have to specify all three of them. And they can be only 1 or 0 or 1. Again, 0 means it's fixed, and 1 means that this coordinate is relaxed. Here we wanted to keep the option laterally fixed for each of these position in the 2D scan of the potential surface, but we want to relax its height. I think the substrate gets fixed just to keep calculations fast. And this way, well, we come to this. So at each lateral position, we have vertically relaxed. So we have optimized the height, and that's why we have only 2 independent variables. So that's 2 lateral coordinates of the options. Again, these are the commands that you can execute. It's better to run remotely because this takes quite a while, because you have this double loop again, and now you do some relaxation and some metallic system and so on. So this was the second. And then the third one was this CO adsorption on rhodium 100. And this, again, it's left as a home exercise. If you have time, if you are interested, you can do it at the end of this session. We are there to help you if you want. And you will see that you will get some other properties. We can get the density differences, so-called. So this is to analyze how the how the density, electron density changes when you adsorb, in this case, the CO on the surface. This is then a different quantity. This is kind of energy result change in the electron density. So from this is not the difference, but you could calculate also the difference in this way. So we take energy range and we calculate all the orbitals that contribute to the density in that energy range, because we have all the eigenvalues and all the K points. So this is another example that you will be calculating. And then you will have the projected density of states, which was calculated already before. And then we have some additional, more complicated way of doing the projection. Here we project the wave functions in our system. So in this case, the adsorbed CO on the metal to the orbitals of the free molecule. And this is again, can be used to analyze how the chemistry changes upon this adsorption. So this is another quantity which is nowadays implemented, and it's, well, I would say relatively easy to use. So you will see in the inputs if you come that far. If you don't manage to do it today, no worries, you can do that later. I mean, either later during this week or then later in your home computing cluster or on another machine. But this is again for the analysis. And then this is, yeah, the molecular orbitals of the carbon monoxide. So this is the adsorbate. And so the projection here, these are the different orbitals. So for each orbital, you would get its own graph, and they all depend on the energy. So for each orbital V, you have this curve as a function of energy. If you have any questions on these quantities, again, this is meant as a kind of advanced properties. And this also shows the advanced methods that you can use with PWTK. So now I'm gone through all the exercises. Now it's time for you to start playing. If you haven't done it yet, you can start playing. Again, we will be there to guide you, to help you. If you have any questions, comments, I don't know, we take now. Soon we will stop the streaming. So this is your last chance. If you have any questions at this point, those who are registered, we will remain there on the Zoom and Slack. But if anyone is there,
okay. So Ari, thank you very much for this wonderful presentation with all these details for practical exercise. So I think we can close the session now, and we can all meet in Slacks to follow the exercise, or for any problem or questions and so on. All the tutors will be there, and also I guess Ari. For those who are streaming, maybe they can ask some questions. There will be also tutor there. So thank you very much, and see you on Slack. Thank you.
thank you.
Thank you very much. Goodbye.
Bye again. Bye.
Bye-bye.
Thank you, Tom. Thank you again.
Thank you very much. Thank you. Bye. See you.
So we will lose the Zoom, right?
I don't know.
I mean,
Ivan.
No. We leave the Zoom on.
Yeah,
We leave
yeah.
the Zoom on.